So without further ado, I would like to call Dr. Fatimah to present her talk today. But before that, if you have any questions, you can type in the chat session. Dr. Fatimah will answer later, or you can answer after her session ends. So without further ado, I would like to call upon Dr. Fatimah to present her talk today.
Assalamualaikum and a very good morning to all of you. Thank you, Dr. Cheputi, for the kind introductions. Today I'm going to share with you a little bit part of my research project, which is, let me present first, which is entitled Time Dependence Density Functional Theory Approach, TDDFT, for solving a stereochemical puzzle. So it is actually a mouthful, but I will try my best to make it in a layman manner for easy for you to understand. Okay, so basically, I'm a research fellow at Atta Rahman Institute. Let me introduce a little bit on our institute. So it is actually located at the 9th floor of the FF3 building here. So if you come from the first door here, so that is the roundabout. So actually this crease is pointing on the institute here. So the whole 9th floor is where the Orient is located. And I'm also senior lecturer at Center of Foundation Study, which is located at UITM campus Dengkia. Okay, so basically, my work covered isolation of natural product from plants. So why we are interested in plant, because the plant has been instrumental in discovery of natural product into a drug. So for instance, we have the salicylic acid, which is came from the weeping willow bark, where actually it's been modified into aspirin, used until now for painkiller. Then we also have pokok kemunting Cina, which have the scientists have isolated compound vinblastine, which is the chemotherapy drug. Okay, and then we also have cocaine, which is a numbing agent from the coca leaf, and we have the pilocarpine, which is a stimulant for saliva and sweet secretion used in the medical field, came from Maranham Jabodi. And last but not least, we have many more, but this is quite important as well. We have quinine, which is used against malaria, isolated from fever tree. So now we have, there are several more being used, but due to the side effect on the quinines, so we have now we have the chloroquine and hydroxychloroquine, which is also been is a candidate for the COVID-19 clinical trials. Okay, so this is all the chemicals. We're going to call it chemicals because it is a chemical. So this is actually secondary metabolites that have been isolated from the plants. Okay, so why actually plant produce chemicals? There are three reasons. First is as a build-up structure, we call it primary metabolites. And it is actually used for physical, chemical, and biological functioning, which is also called physiological. So for instance, we have a carbohydrate. So this carbohydrate, we have carbohydrate molecules, cross I pointed up here. So it is used in the photosynthesis of the plant, where actually the carbon dioxide is produced and the oxygen being produced, and we are consuming that. And for physical defense means that the plant has spines, thorns, hairs, and waxes. So the examples of waxes that we have is suberin. So suberin, this is the structure of suberin. It is it's a polymer. So it is a type of waxes that produced by plant for a defense mechanism. So for instance, we have a jackfruit here. So for the unripe jackfruit, it will produce these waxes. It is actually preventing us to take it, and the animal to take it before it fully ripened. Then the last one is for the chemical defense. This is secondary metabolites, the one that I discussed a little bit just now. So we have a bold taste, which is due to limonene in lemon, and also we have a citric acid. So this is actually for chemical defense. It is preventing the animals to take it. And then we also have polygon. So this is from mint. So it produces a smell. So actually it want to repel the insect or animal to come near to the plant. Then we also have tannin. This one, another example, if you have come across into ripened banana, so you're going to see all the black spots. So this black spots is actually due to the production of this particular compound, tannin. The function of the tannin is for the defense against microbial contamination towards the fruit because it is getting older. And then other examples of using this chemical defense is for electrical impulses, hypersensitive response. So this is actually towards the killing, kill in infected cells. For examples on the tannin just now. Okay, so how actually we, natural product chemists, isolate and elucidate the chemical from the plant. So it is actually not an easy task, where it is like pulling out a golden needle from a haystack. So it is not an easy task to do, but basically it is achievable, and we need a strategy to do that. So for this one, the one that I'm going to discuss here, we have a plan. So this is the plan that I worked during my PhD back in 2010s. So the plant is Uncaria longiflora. So if you remember, you know the Gambi. So this is under the same genus. So we dried the plant. How you're going to dry the plant is depends on what type of compounds that you want to focus on. If you are focusing on essential oil, then you have to analyze the sample fresh. If you're focusing on the slightly sensitive compounds, you should just air dry it, and if it is a quite robust compound inside there, so you can use the oven dry. But for my case, I just air dry until all the water evaporated. The water evaporated from the samples. So then we grind the samples. So the purpose of grinding the sample is because we want to increase the interaction between the solvent, the extractor solvent that we're going to use, and the extract as well. So most of the compound will come out to the extract. So this is like when you try to make your own tea. So you put your tea in a hot water section. So the color will change. The water, the color of the tea will change. So that's going to become the extract. So similar like this one, but we are using organic solvent for this case. So after getting the extract, we evaporate off the solvents by using rotary evaporator. It depends on a type of solvent. If you have water, then you have to freeze and dry it in order to get the extract. The features of the extract will be depends on what is inside there. If you have a sticky, most of your compound inside the extract is lipid or oil, so you're going to have a slightly sticky extract. But for this one is dry. After that, we need to fractionate first and profile by using HPLC. So this is quite important to see what is the degree of complexity of metabolites or chemicals that you have inside your samples, to give you an idea. Actually, before we start doing we choose the plant that we want to study, we already have an idea based on the traditional uses, or we did literature review on what type of compound that we are going to deal with. So that's going to be a guidance for us to choose the right solvent system and the extraction procedure in order to get the exact type of compound that we want. After that, we're going to purify our compound, isolate, fractionate, and then purify it. This will take a long procedure, but if we have a very strategized manner of doing this, then it will be achievable. Will take quite short time compared to the conventional technique. So this type of compound it undergo a recycling HPLC. So after purifying the compound, we're going to have this type of the appearance, or the physical appearance of the compound will be like this. It didn't finish here because you need to know what is exactly a chemical component that giving this feature of the structure of, the physical properties of this particular substance here. So we have to use all the spectroscopic techniques, which is actually we have light dealing with our particle inside here in order to get the structure. So here come the expertise on the chemists, phytochemists. So we run the NMR first. We're going to have this spectrum. So the NMR will give you information on type of, hydrogen and carbon that we have in our structure. And then it also will going to give us information on the chemical environment of the carbon and hydrogen there, and their which particular hydrogen is neighboring to which particular hydrogen and carbon as well. So this will give us an idea actually of how the structure of the molecule been organized or put together inside before becoming a molecule. And then we run the UV. So UV will give us information on type of chromophore, a group of electronic transition that you have in the structure. And then that going to be complemented by the IR spectroscopy. This will give the information on the functional group. So what type of functional group that we going to have inside the structure. And then this is the mass. So the mass will give us information on the molecular ion weight of our samples. And if we have a chiral compounds, in that you have a 3D, different 3D arrangement of the carbon or hydrogen or atom inside the molecule, then we have to run the CD. So this is going to be, finally, you're going to get this particular structure of here. Okay, but if you have a planar compound, it's okay, it's going to be finished. But if you have a 3D structure, which is, we call it chiral. Chiral means that you have a structure, a chemical structure, which is all the atoms been arranged in a similar manner, but you have a different orientation in space. We call it spatial orientation arrangement. So by putting the for instance, you have this particular hydrogen here. By putting this particular hydrogen nearby this carbonyl group, this will influence the chemical environment of this particular hydrogen. So different chemical shift that you're going to obtain in your NMR. And when this particular carbon here is carbon 7 here, changes in the orientation, different configuration. So this benzene will become nearby your hydrogen here. Then your hydrogen will shift at the different chemical shift that this will give you an idea actually the configuration of the structure. So why actually we need to determine the molecular configuration? Why is it important? So if you remember the thalidomide tragedy, which is actually forced the drug company to consider enantiomers into a separate molecule rather than different form of a drug. So this is a thalidomide structure. Thalidomide is an alkaloid. So we have a chiral center here. So chiral center here means that you have an atom which have different properties of a group of elements that bonded to it. So this will cause the orientation in space. So if it is in 3D, you will see that this bold dash is showing that this particular moiety is facing towards you. So out of the plane, we call it. And then for this one, you have the bond like wedge here. So this is showing that this particular moiety here is going into the plane, facing into you in the 3D manner. So what about this thalidomide? So this thalidomide, which is the other thalidomide, is been prescribed for as an anti-nausea for pregnant women. So it is actually a sedative. But the chemists the chemists, they don't know, and the pharmacists, all the drug company, they don't know that actually the S thalidomide, because of they call it S because of the rotation at the nitrogen center is sinister, means that towards the left, moving towards the left. R means that it is moving to the right. This is rectus. Okay, so they don't know that this S thalidomide actually is a toxic. So it is a tetragenic, causing baby to deform. So at that year, more than 10K babies born were having birth defects. So this is called phocomelia. So after they identify that actually that is due to the other isomer, which is the ISS isomer of thalidomide, then the drug been withdrawn from the market in 1971. So they have to separate these two drugs into different molecules in order to prescribe it to the patients. Okay, before that, this is quite important as well, very fundamental. So since I used the words stereochemical, so stereochemicals means you have a chemical, a substance, we call it chemical, with a stereo property. Stereo means you have a similar orientation of all of the carbon, but in space it is different, like this one. So you have, this is out of the plane, this is into the plane. So how are we going to identify how much or how many type of isomers? We call it isomers because they are same orientation but different properties, spatial properties. So we'll call it isomers, stereoisomers. So that going to give you 2 to the power of the chiral center. Means that if you have one chiral center, so the possible number of compound that can be formed from that particular arrangement is going to be 2. So this is because you have one chiral center, so you're going to have 2 to the power of 1. So 2 possible compound. A new molecule just now, because we isolated the compound as a natural product chemist, and then we need to establish the configuration. So this is going to be an example of in this work how actually we solve the puzzle by using quantum mechanical calculation. So this is the drug, not the drug, it's a compound that been isolated from the Uncaria as well, the one that I work during my PhD. So this particular compound, apart from other 12 similar type of compound, we also got this one. This is the isoformosanol and the formosanol. So the difference between this compound is at the C7. So that's why you don't have the dash and the wedge here, because they have different orientation at this particular center. I will explain to you later by referring to another quietly similar related structure. And then, as I mentioned before, in order to know how many possible compounds that this particular structure can form, we have to know how many chiral center that we have. So for the thalidomide structure, the nitrogen become the chiral center. But for this one, this is carbon. So this particular carbon is also bonded to 4 different properties of group of substance. Then it will become a chiral center, means that you have different molecular weights, so it is capable to rotate, whether to the right, R we call it rectus, or to the left, which is S. So since this one we have 1, 2, 3, 4, 5, 6, 7. So we have 7 chiral center, means that 2 to the power of 7. This means that the possible number of compounds or chemicals from this particular skeleton is capable to form 128 different molecules. So that is very, I mean, that is too many. For this one, this is also the compounds that have been isolated from the same plant. If you can see here, the difference between this and this is actually, it is just like been cut here. So we are proposing that this particular compound it came from the biogenesis. Biogenesis means in the plant, because the plant is a living cell. So it also have it's just like a factory of producing chemicals. So there is a command based on the gene arrangement in the in a very principal manner. So each particular plant will produce a similar group of compound due to this similar genetic code, genetic information that they have. So this is a type of alkaloid. So it is called the oxindole alkaloid because we have the amide moiety here. So they came from the biogenesis of tryptamine inside the plant. So for this one, this part that is came from the cycloganin. It is a monoterpene moiety. So they combine together in a systematic manner in a command of the gene order to become this particular compound. So for this one, it is actually haven't finished to become the full structure, but during the collection of the samples, so we managed to collect it at that stage. So all the process stopped at this stage. So we managed to get this part of the compound. So for this one, it possesses 1, 2, and 3 chiral centers. So this means that this compound are capable to form 8 different molecules. So we're going to have 8 different molecules. So we are into this group of compounds because we thought that it is potential to be developed into a lead compound. because they are biogenetically related to other chiral compound, monoterpene-derived drug as well that we have in market. This is Respirine and this is Ajmalicin, which is being used in the hypertensive drug. So there are a few methods that have been used to determine the configuration of a molecule. Among the techniques that have been used are the X-ray crystallography. So X-ray, we do have our X-ray system in our RIN. So the problem with the X-ray crystallography is it is a relative technique because you need to have your sample in a solid state, which is in a crystal form. So if you have a very good crystal, you can run your X-ray crystallography, but still you need information on the probable type of structure that you have there, and there come the information on your literature review. And we also can use spectroscopic method, which is including the nuclear magnetic resonance. So most of this is using the derivatization using Mosher methods. We also can use chemical correlation methods. So chemical correlation methods is actually, you already have a well-established structure related to your particular structure. And then we're going to refer to all the chemical shift, all the spectroscopic data, all the spectrum information in order to compare. So we're going to compare the data, the information of the compounds to the one that we have. Then we can derive the structure, the configuration based on the one that already been established. And we can also use Raman optical activity. So Raman optical activity is based on the light scattering. So different type of way of interaction of light, the compound and the light as well. And the most sophisticated techniques that been used, which is very sensitive, is the circular dichroism technique. So here we are also interacting our sample with the light, but it is the if you are familiar with polarimeter, so the polarimeter, we only use one type of light where the light been polarized. But this one, after the light been polarized in the polarimeter, we have another monochromator. We have a polychromator, which is actually converting the polarized light into circular light. So you're going to have your left circular light and the right circular light. So these two type of light are going to interact with our chiral compound in order to get the interaction. If our compound going to absorb more of the light, circular light, so the left will appear more. So left going to be negative. And if our compound absorb more of the left circular light, so the right circular light will appear more in the spectrum. So you're going to have a positive sign there. So there are two. We have it in UITM actually. For the vibrational, this is the only instrument that we have in Malaysia, and it is located in Faculty of Science Gunaan, Shah Alam. And then the electronic circular dichroism, this is based on the, when you talk about electronic, we are talking about the electronic transition. So the type of energy that been utilized towards our compound is the UV light. So the UV going to be between 200 to 400 nanometer. And for the vibrational circular dichroism, the light source will be the IR. This is the energy. The energy is not enough to excite the electron. It is only enough to vibrate, giving vibration. So this is very crucial for your chiral center that nearby a strong functional group inside there. For instance, you have carbonyl. So these two are the most sensitive technique that we have now. Okay. But the problem with the circular dichroism technique, it has a limitation because it is actually comparisons. So it largely depends on the comparison of the CD spectra by enantiomers or diastromers. Means that you need to have a series of compounds that have relatively similar structure, and then you're going to run the experiment and look at the spectrum and compare between the structure and the spectrum to derive the exact correlation between this structure as well as the spectrum. And the other problem is actually it is actually it is difficult to assign the CD signal towards the molecular structure because most of the signal will be overlapping, especially in the ECD, electronic circular dichroism, because all of the type of the electronic transition will come together if the environment is similar. So they come the quantum mechanical calculation. So I put it there. So this particular method, it is a simulation method the purpose of doing that is we are modeling. We are modeling the spectroscopic data of our compound, the one that we want to find the configuration in by using a mathematical formula. So the most common method that we use in the ECD is TDDFT, time dependence density functional theory. So this is based on the density of the electrons surrounding our atom, and all the atom that form bonding together to form the molecules. So I believe you heard as well the DFT. So DFT is density functional theory. So the difference between TDDFT and DFT alone, DFT is we are acquiring the data in the ground state manner of the carbon, the atoms. For the TDDFT, this is in the excited state. So for the vibrational circular dichroism, we're going to use DFT, and for the electronic circular dichroism, we're going to use TDDFT. So TDDFT will consume more energy, more time upon the calculation, because we are dealing with the electron which is in the excited state. So as I said, this will be achieved by solving certain level of complexity. So we have to understand actually, but I will explain that later. So when we have the CD signals of that we have in the experimental, and then we have the one that we already modeled, so we simulate the data by using quantum mechanical calculation. So we're going to compare these two data, these two spectrums. So the two spectrum that have the higher degree of similarity, means that they overlap very close together, that will show that the one that the structure that we draw, that we propose in our quantum calculation is similar with the one that we already elucidated. So this will help in the determination of the absolute configuration of our chiral compound. So a little bit introduction on the quantum mechanical calculation. So it is actually a theory that shows the individual behavior. So it is a theoretical things that showing the individual behavior of subatomic particles. Subatomic particles, if you still remember your basic chemistry and physics, in an atom you have a nucleus inside there. So inside the nucleus you have neutron and proton. So that is the particle. And you have an electron which is moving at the higher energy surrounding the atom. So these three, we call it subatomic particles. So we want to look at this behavior of this particle inside the compound in order for us to simulate or execute the spectroscopic data, which is here is the circular dichroism. So the aim of this one is to describe the property of the matter. Of course, our compound, just not the chiral compound, from the theoretical method, which is rooted in the fundamental equation. So the mathematical equation should be precisely chosen to make sure that the data that we're going to simulate is mimicking the one that we have in the experimental data acquisition. So what is basically being done here is we have experimental data. Okay, it doesn't matter what type of data that you want. It depends on what are you looking for? What do you want? What information that you are acquiring? So we're going to, after the experimental data, we propose the structure. So we're going to put it in the computer. We draw the structure there and let the computer work, but you have to use the right mathematical function inside there. So they will give us information on the material properties. So there are millions of information that you can get, but for the chemists, we are very interested in looking at the electronic properties. So we can see actually the HUMO to LUMO electronic transition, because we are dealing with TDDFT. So we can see each particular electronic transition is due to which particular orbitals inside the molecule. So you also can get the information on the magnetic property. So magnetic property of our compound, we can get the optical property, means that you can get the optical, the polarimeter, I mean the alpha D optical property. And then we also can get the vibrational property, means that we can know the type of bonding, whether it is stretching or it is actually stretching, bending, and it is asymmetric or not symmetric as well. So all of this information we can use to to derive our molecular structure. So that is how actually the puzzle is being done. So basically, what I'm going to show to you today is the overview of the presentation. Going to be all of that was the introduction part. So this is going to be the content, right? So in order to establish a quantum mechanical calculations, we need to have a very good, a well-established molecular structure, that you know the absolute configuration, that you know the molecular structure. So we're going to exploit this particular structure in order to get the representative level of theory in order to be used to other related molecules. So this is the two molecules that we have. We know the structure already. This is not arbitrary anymore. We draw the molecule in the in the software, and then we give the orbitals, we give the property of them, with the diffusion, the effusion as well. So you have to know that you really need to understand your structure here, where you know that your structure contain an electronegative atom, which is for here you have oxygen and nitrogen. So the ability of the oxygen to withdraw the electron from the nitrogen and other carbon inside there will affect actually the chemical environment inside here, the data they're going to produce. Then you have the basic nitrogen here, that is the acidic nitrogen. You have the basic nitrogen there, that going to also influence the environment of the carbon and hydrogen inside here in order to give the different electronic transition property. So you really need to understand these two compounds first in the chemistry wise before you decide which particular method in the quantum mechanical calculation that you want to use. So the important part here is actually the basis sets, the solvation models, and the exchange correlation functional. But because this calculation, TDDFT, is dealing with a very detailed information, so it will consume more time and cost in the calculation. For calculating the CD, it will take days of months as well for you to get the exact data. It depends on the capability of the computer that been used. If you have a supercomputer, then the data can be you can get the data in one day. But if you don't have that strong computer, the one that we are using is actually it's not a supercomputer, it's just a high performance computer. So that was bought, I think, about 15K, and we still can get the data in 5 days like that. So we need to balance between the time and the cost. So our purpose is actually, when we're going to run the experimental circular dichroism data inside the spectrometer here. This is our CD, so we put the sample to get the spectrum, the CD spectrum, and then we're going to have this one. This is the black color, is the one that the experimental one, and we're going to exploit this structure in order to get the best basis set, the combination between solvation model and then the exchange correlation functional, until we get a similar properties of absorption, which can show that the method that you're using is actually a good one. So the metrics that are combining the basis sets, the solvation model, and the exchange correlation function is called the level of theory. So the best level of theory will be used to calculate the absolute configuration of the new 3 compounds that we have in hand. So this is to show, to verify actually the method that we already developed, the level of theory that we already developed is reliable. So upon having a good correlation between the experimental and the theoretical, that will establish the absolute configuration of these 3 compounds. As I said, we have to know the chemistry of our structure. So in the circular dichroism spectra, it is actually absorption, because we are dealing with electronic transition. So if you have an idea on the UV visibles, so it is the same energy being used, but the light being polarized in a circular manner. So you're going to have your positive circular polarized light and negative circular polarized light. The interaction of our compounds towards the lights will give us this spectrum. So if our samples here absorb more of the negative circular left, I call it left, which is negative, the left circular polarized light. So the positive or the right circular polarized light will appear more, and vice versa to if the compound absorbs more of the right circular polarized light, so the left will appear more. And if you can see here, you have a slightly less, like this one, you have a very, it is negative, but the value is less. This is because of the moiety that we are referring to. They actually are absorbing both left and right circular polarized light. But since they it absorbs slightly more of the right circular polarized light, so you will get a little bit on the left circular polarized light detected by our CD detector. Okay, so it is absorption versus the wavelength. So this is the UV. So the data acquisition was obtained by using wavelength of 195 to 315. So if we use this one, so you have to be careful in choosing the right solvent in getting the experimental data, because we didn't want the solvent cutoff interfere with our crucial absorption here. So for these two compounds, I want to show with you the chemistry behind it. So between these two compounds that we exploit actually to get the best level of theory in order to be used on the new compound just now. So we choose them because they are related, the structure is related to the previous one. Their electronic transition or the chromophore are similar, slightly different here. Okay, so between these two compounds, this is isotherapodine, this is therapodine. Okay, they are only differ at this particular chiral center at carbon number 7. If you can see here, okay, this is the oxindole moiety. So it is an amide. So this amide is going into the plane. So going down here, that's why you have the wedges. So it is actually facing, it's going inside you. If you are looking at the screen now, it is going inside you in the 3D manner. So for this one, for the therapodine, the oxindole moiety is actually facing out of you. So in the 3D manner, it is facing there. And as I mentioned just now, by changing the orientation here, we're going to expose the electronic environment of the chiral centers here, there, and then you have here, there, with different chemical environment. Means that the things that I usually share with my students is when you sit, I'm sit at and blow near the aircon. Directly, I'm sitting under the aircon, and my student is sitting on the other side of the aircon. So I'm going to experience more of the aircon compared to my student. So the aircon is actually the amount, the electronic environment that been the electronic environment that we have inside the molecule. So the electronic environment that we have here is due to this benzene ring. So for the benzene ring, we have 3 types of absorption actually, which is going to be here at 200, and then we're going to have at the 255, and then we also get at the 275 absorption. But the butterchromic mean shift to the right, the red light, or to the left, which is the strong light, the blue light, is depends on the other properties that influence them, which is of course the polarity of the atoms involving there, as well that will cause the diffusion and effusion of the electron cloud. So for this one, because I highlighted this region, so this particular region, if you can see here, between these two compounds, the difference in the absorption is actually at this region. That one become negative, this is positive. You have similar absorption here, still positive, positive. And then this one is still negative and negative. And this one, this is negative and that is positive. So the negative, positive, all of this thing, we call it Cartan effect. So we understand that actually this particular absorption here and that particular absorption there is actually due to this oxindole moiety, because the only changes between these two compounds is here. So upon changing in the orientation, the absorption will also change at these two regions only, not here. So we decide that the absorption at 235 and 255 is actually due to this the pi to pi transition, because you need to transit the electron to the highest step, so that is pi star. So pi to pi star transition, and you have a lone pair here, which is due to the lone pair of the oxygens, the ester moiety. This is called the alpha beta unsaturated carbonyl methyl ester system. So this region will give you these two absorption. So by understanding this one, we know that in the quantum-wise letter, we know that which particular region that we need is crucial, and we need to refer to the best. And this is also important for us to decide which type of mathematical formula of in the theory that we want to embed inside. So we didn't start from the scratch, because you're going to have thousands of mathematical formula in the TDDFT to be chosen. So this will reduce focus on which particular exchange functional you need to use. Okay, so basically, this is how the stereochemical puzzle been solved. It is, it is a lot of work that been done. So this is done in 2 years by my master student. So it involves 3 major parts. The first one is the experimental part. So we purify the compound. The compound need to be purified, highly pure, because CD is very sensitive, as I mentioned before. So if you have an impurity inside there, the spectrum will give you a data that actually slightly changes from the one that you should have. So it will reduce the information that you can get from the spectrum. So you need to have it in a pure form. So we use recycling HPLC because recycling can give a high purity of compounds. So it's about 99.9% purity. After getting the compound, the physical compound, so we need to characterize it again by using NMR is enough, because we already know which is which, but we want to confirm that the one that we run into the CD spectrophotometer is the one that we are referring to. Means the isotherapodine should be isotherapodine, and therapodine should be therapodine. The other part is the quantum part. This is actually the most consuming, time-consuming part, where it actually involving in the optimization of the level of theory. So it started from drawing the 3D structure in Spartan. So we use 2 types of software, which is Spartan as well as the Gaussian. So we use Gaussian 9. So this pattern, the 3D structure of the compound, so we have 2 compounds just now. So we draw the 3D structure in this pattern in order to get the conformers, because during the data acquisition, you're going to imagine that because it's a 3D compound, so we're going to imagine that it is swimming inside the solvent. So it depends on the stability of the compound. So which is more stable will form more. So that is located, they combined in a form of Boltzmann distribution. The higher Boltzmann distribution will give the more stable compound. So it is actually swimming, changing only conformation, not configuration. So configuration is different than conformation. You already have configuration, means that you are facing out of the plane, but it will slightly change to the left or the right. So that is called the conformation. So after getting all the possible conformers by using this one, I will share with you later how we did this. We're going to optimize the structure. So the structure needs to be optimized in order to get a more stable conformers or structure. We didn't want the structure keep changing, the energy is high. We want to reduce the energy so it will become as rigid as possible for us to acquire the CD data later. And then after getting the optimized structure, we need to optimize the level of theory. So the level of theory, as I told you before, that is actually consisting of, it is a matrix actually consisting of basis sets, solvation effect, and exchange functional correlation. So these 3 are very important to be embedded in the level of theory. So here we choose a few basis sets, solvation models, and then the exchange functional correlation. So this is why I mean the how you decide to choose this one. This is based on literature review. Of course, you have to find a literature that done on the structure that related, slightly related, because for this particular compound, there is no study that been done before on determining the quantum, determining the theoretical CD calculation for the particular compound. But there is a related compound which is also an alkaloid inside there, so we use that one in the study. So after that, we calculate we choose only one conformer, because if you want to try everything, that they will consume time. So we need to be strategized here. So we choose one conformer, and then we calculate the CD data. After getting the CD data, we compare with the experimental one. So we have experimental spectrum and the calculated spectrum. Upon having a good correlation, that we're going to proceed with the other conformers for all of the two compounds. And if the degree of similarity between the experimental and the theoretical spectra is bad, then we have to discard the method. So after calculating all of the compounds, then we got the good correlation, so that will become the best level of theory. So this is the one that we are seeking for or searching for. So upon getting that one, we can use the level of theory to verify it by using the new compound that we have in hand, because their skeleton is similar with the one that we used to establish this particular method. So they should be suitable to execute the CD property for the three new compounds. And that is if it is good. So the method is good, you're going to finish, then get the absolute configuration of the structure. But if it is bad, then we have to re-characterize the structure. Means that the one that we proposed before, the structure that we proposed based on the spectroscopic characterization might be wrong. So we need to re-characterize it again. So that is the method verification. So this is how actually the puzzle been solved. So as I said before, I'm going to share with you how the conformational analysis been done. So we choose for the isoterapodine because we have two compounds, terapodine and isoterapodine. They only differ at this particular region, which is the oxindole moiety. So one is into the plane, the other one is out of the plane. So that is executed in the 7S. The other one is 7R. So the rest will be similar. So we draw the structure in Spartan. So Spartan will give all the conformers. Conformers means that they're going to change a little bit in their how they swim inside the solvent. So the one that more stable will have the higher population during the data acquisition. So how we're going to determine the stability is based on the energy exhibited by this particular conformers. So the one that have energy below 2 kilocalorie will be accepted to be further optimized. So for this isoterapodine, we have 4 conformers. Okay, so only 2 conformers that exhibit energy below 2 kilocalorie means that it is more stable during the data acquisition. So the population, the amount of this particular conformers that form is 65.5%. This is 34%. This is 0 and that is 0, but they still can exist there. Then for the terapodine, okay, terapodine you have 7R. Isoterapodine you have 7S, because as I mentioned, they only differ at the chirality or on the carbon 7 here. So similarly, we subject to molecular mechanic force field in the Spartan. So for this one, we have 6 conformers. So though only differ here, but you're going to have different conformers. So this is the beauty of actually how the chemicals is changing inside our solvents there. So the terapodine, for the terapodine, among these 6 conformers, only 2 that are stable, exhibiting energy below 2 kilocalorie with higher population of Boltzmann distribution. So 80% of the conformers is this one, and 19.2% is this one. So we discard the others. And then we optimize the structure. The purpose of, again, optimizing the structure is we want to make sure that the structure is to be rigid as possible, because if it is keep changing in the structure, the conformation is keep changing, then we couldn't get the best chemical environment to be excited during applying the energy, the electronic energy. So the spectrum, we wouldn't get the right spectrum to represent the overall overall properties during the data acquisition. So we have to reduce the energy as low as possible. Means that easy for us to control. It's just like your kids are keep jumping, and we want them to sit down first and then give them, advising them. So this is how the thing should be done. So for isotherapodine and therapodine here now, so one going to be isotherapodine, two going to be the therapodine. Only two conformers each, for both of them was stable. So we refine in the semi-empirical level by using PM3, and then we reduce the energy. We reduce the energy and then further geometrical optimize the structure to get the minimum energy of -7.69 to the power of -5. So this is very slow movement. So now the conformation going to change slightly, but very slow motion. So it's easy for us actually to execute or to get the idea on the electronic environment inside our atom that produce the structures. As I said, the most important characteristic that criteria that we need to have in the level of theory is these three things. The first one is exchange correlation functional. So exchange correlation functional is actually giving information on the total energy of the molecule. So because your molecule have all of these atoms. So for my compound just now, I have carbon, I have hydrogen, I have nitrogen, I have oxygen. So what is the amount of energy that we have here that is embedded in the exchange correlation functionals? So another information that important here is the correlation energy. Means that you already, like this one, we already we want to draw our structure according to the one that we propose in the quantum, in the software. So we have to draw it correctly. We have to make sure that the carbon 3 is next to carbon 4. We cannot put carbon 3 next to carbon 5, or else you wouldn't get the representative quantum CD data for that. And the other information that we have to embed there is actually, we have to make sure that carbon 3 and carbon 4 is communicating, means that they know that they are beside next to each other. So that is the information that we can get in the exchange correlation functional. The other one is the basis set. The basis set is actually the build-up, the heart of it. It is actually we want to build the shape of the orbitals. If you remember your quantum chemistry, each of our atom, they have their own orbitals. So S orbital having a round shape or a circle shape, and then the P orbital going to have a loop shape, and then you have D orbital, you have F orbital, and so forth. Depends on how many electrons that you have. The more electron you inside the atom, the more complicated the orbital will be. So this is very important because you already draw the structure, our structure, but now we want to put all of the orbital inside there. Okay, so for the CD, in order to get the good shape of the orbital, which is including the polarization function, so you will see later the D and the DP inside there. So polarization means that because the structure that I have here is, it consists of electronegative atom, which is nitrogen and oxygen. So we need to polarize, means that we need to concentrate. They have a distinct properties of electronic environment. Between carbon and oxygen is more electronegative. So the orbital should be more towards the oxygen, because oxygen going to withdraw all of the electrons from the carbon. So we need to embed this property inside the molecule. And then the other things that we have to consider is the diffusion function. So you also can see the plus sign or the asterisk is the same thing inside the basis set letter. So that is giving the information on the diffusion function. So the diffusion function is also very important because during the data acquisition inside our CD, you put a sample inside the CD. Actually, the sample it is not containing only one single molecule. It's containing thousands of molecules, which is actually interacting between each other, whether in a form of intramolecular or intermolecular or within the solvent itself. So they are forming hydrogen bond there. So you have to embed that in the basis set. So this is important criteria that you have to choose. So you have to understand the chemistry of your structure. Okay, the other things, the final one is actually the solvent effect. As for the CD, the data been get in the solvent. So we put our sample in the solvent that the compound can dissolve. You have to make sure the compound is totally dissolved. Or if it is not dissolved, then you cannot get the data because there is no physical interaction between the solvent and the compound. So you wouldn't get the spectrum inside there. So the purpose of embedding the solvent effect is actually we want to reformulate the environment of the molecule, which can affect the magnetic dipole moment. As I mentioned before, our molecule and my molecule just now, because they have a polarity, a diffusion due to the different atoms inside there, especially nitrogen and oxygen. So they're going to form a delta minus and delta plus region. So that is what we call polarity. So the delta plus region of the compound will interact with the delta minus of the solvent, and the delta minus of the compound will interact with the delta plus of the solvent. So this will cause induction on the geometrical distortion, means that the structure can become slightly, the structure, the bond will become structured, or it become closer towards each other. Depends on the strength of the electrostatic between the positive and the negative side of the molecule and the solvent. And this will eventually causes indirect change in the rotary strength. The rotatory strength is very important in the CD because we want to get the rotation, because the rotation will occur during the data acquisition. So we have to make sure that the rotation strength is enough actually to execute the data inside there. So among the solvent method that we use, the famous one is actually IEFPCM. So the current best solvent method that we use so far. And combination between a H correlation functional, the basis set, and the solvent effect is embedded in a matrix called level of theory. So this is the things that we want to find. After finding the level of theory, then we can use the level of theory to obtain or to simulate or to remodel the CD spectrum of our new compound in hand just now. And the best combination between these three, because we need to find the best combination between them. Try and error, no. You have to have the idea by literature review and understanding the chemistry of your structure. So this will execute the accurate CD spectra during the calculation. Okay. So we choose one of the conformer. This is I1. So I1 is the isotropodine. We choose the less populated conformer. Why we choose the less populated conformer? Because it is very small. I mean, the population is very less inside there. So when they are very less, so easy for us to identify or to know to be affected. So we use this one, and then we calculate the CD by using TDDFT by changing the basis set. So we choose 6 series of six different basis sets. Whether we include the diffusion, or we didn't include, and we include the polarization, or we didn't include it. We want to know actually which is the best one, but we have to be careful because the more complex the basis set, the more time consuming the experiment will take. So we need to balance that one as well. And for the solvent effect, we choose ICPCM because that is the best one, but we also choose the other one to compare. And because some of the experiment for the compound, they also can get a good data in the gas state. So we also include the gas state to become the standard. But because we really understand our structure, so this compound is polar. When it is polar, so we need to include this solvent effect actually. For the gas state, this is the gas state can be applied for compound which is not non-polar. So if you have non-polar, the solvent wouldn't interact with your compound, that you can use the gas state. It will still give you information because gas state will take less time in the calculation compared to the solvent effect as well, because there are more detailed information that you can get. For the functional, we combine between the hybrid functional and the ordinary functional, the non-hybrid one. And we also include the most common. So B3LIP is the most common exchange functional that being used, but we also include the long range correlation. We use the long range correlation because we know that our compound is actually in a conformational manner. This one, as you can see here, when they conform, this moiety will be close to the other moiety. So there is possible electronic transition occur between them. So we also include that one, though it will take more time. So again, when changing between these three information, I mean, to find the best level of theory, combination between them will give us the best level of theory. So we can use the best level of theory for the remaining conformers that need to be calculated. Okay, so here I'm going to share with you how actually the best basis set they've been obtained. So if you see here, the one that been aligned in a dotted form, this is the experimental data, the CD just now that I explained in detail, which particular absorption is which particular moiety inside the structure. So we calculate with the without diffusion and effusion. So this is without diffusion and diffusion, and we got mean absolute error, which is quite high, 0.18, and then we include the polarization. This is a the asterisk is similar as this is the polarization function. This is the diffusion function. That is the polarization. So the plus is similar with dp. Okay, so we also include this is the polarization. This is the diffusion. So between the depolarization and diffusion, we see that the mean percent error between the data is reduced, and then we try to include both. We include the polarization and the diffusion, and the error become more or less, means that it is producing more or closely similar spectrum with the one that we have here. If you can see here, this one. So this is the one that color in orange. So this one, okay, it is close to our compound actually here, if you can see there. But if we include more diffusion function there with two asterisks, we can see that the error become more smaller. So it become smaller at this stage, at this one, okay. And then if we increase more of the more detailed information on the core electron and the valence electron, this is information on the electronic environment for core and valence electron, we see that the error becomes 0. So this is the best actually, but because this will take more time in the calculation, consuming, for instance, this one you calculate it in 1 day, this one you need to calculate in 5 days. It depends on the performance of the computer. So we choose this one. We choose this particular basis set. So for the solvation method, we already put the best basis set. For this one, in order to get the best basis set, we use the most common exchange functional in the natural product, which is the B3LIP. And then we use the most common solvent effect in order to get the best basis sets. So after getting the best basis sets, then we have to change the solvation model, which is the best, but we are still using the B3LIP because this is the most common that being used in natural product. So by using all of this one, the indicator will be the mean absolute error here, okay, and that is shown by the degree of similarity between the experimental and the calculated form. If you can see here, the guess state, this is the guess state. So the guess state is deviated far from the experimental one, because as I mentioned before, our compound is a polar substance, so it should be calculated in the liquid form. I mean, you have to include the solvent form, because the solvent can reduce the interaction just now that as I mentioned before. So we cannot use guess state for this one, but it's okay to try in order to make sure that we are in the right track. Okay. So between these three, of course, ICPCM is the best because it gives us the lowest mean absolute error. So there is the one that been colored in red. So you can see here the experimental and the theoretical is closely to each other. So now we already have the best basis set and the best solvent model. So we embed in the level of theory. Now we want to find the best functional. So the best functional is very important because we need to make sure that the atom is communicating, and we know that each particular atom is exchange their information in the form of electronic based on the electrostatic behavior of each of the atom. This is very basic chemistry. The electron is always attracted to a nucleus which contains proton. So whether the proton is from its own proton or from the adjacent or nearby proton in space. So that can happen. Okay. So between these two, between all of the functional being choose, you can see this is the non-hybrid. So the non-hybrid is not good because it's giving the high error here. it couldn't reproduce our crucial Cartan effect that we need in our structure. So that is the case. You can see for the non-hybrid BP6 at 6, you can see that the spectrum is deviated from the experimental, which is in the dot form. Okay, so actually the dot form is very closely very similar in the bit-relip experimental data. If you can see that, that's why you cannot see it clearly because it is embedded. So this means that they are very close together. And between these two, we also include the chem-bit-relip because this is only for one conformer. We have many more conformers for the two compounds. So we also include the chem-bit-relip because, as I said, in our structure just now, we know that there are possible changing of the electron in space. Interaction can occur due to the conformation change of the compound. So we choose these two based on the lower mean absolute error that been produced. Okay, so the base level of theory we have two now. So the difference between this particular level of theory to that particular level of theory, their basis set is similar, their solvent effect is similar, but the exchange functional is different. We want to try. So we calculate all of the conformers that we have in hand now. So 2 is for the isotherapodine and another 2 is for the therapodine. Now, look at this one. So for the isotherapodine, we don't have problem for the isotherapodine because bit-relip can actually produce a very good or very similar, high degree of similarity with our experimental one. Okay. And then for chem-bit-relip, also it can produce, but slightly overestimated in the intensity. So overestimation in the intensity is usually happen in the long range because we are considering the interaction between, changing between information, long range information between the carbon. So this is actually common happening in the chem-bit-relip. Okay. So for isotherapodine, we don't have problem because they are similar. Means that this particular absorption is still positive, you have still going positive, and then negative, and then you have the negative side there. But for the therapodine, if you can see here in the bit-relip, this is the crucial region because we know that this particular region just now is due to the N2 pi transition of the oxidal moiety, the amide group there. So this is crucial, and this is also crucial to give the information. But for the bit-relip, it failed to produce this particular absorption. It actually produced a negative absorption, which is wrong. So it couldn't produce the Cartan effect at this D region. So we already assigned A, B, C, D Cartan effect for to ease in the determining the structure. What I'm trying to say is actually this particular moiety, the electron that we have in O and the nitrogen is not able to be produced by this particular. The electronic transition is not able to be produced by the bit-relip. Where in the chem-bit-relip, it managed to produce. We have positive there, and we also have positive there. Though we have a shift in the hypsochromic shift, which is a blue shift a little bit on towards the left. It's because of the the long range is happening, but we need to to upgrade a little bit in the mathematical formula to represent the total the total of the correct environment of the molecule. But this is depends on the molecule itself. But the other been properly predicted. So the absorption at this region is still negative. Overestimation, as I mentioned just now, is okay for that. Then still negative, although overestimation, a little bit of hypsochromic. Hypsochromic means shift to the left. Bathochromic was the right. And then the higher intensity, we call it hyperchromic. And then if it is slightly down here, we call it hypsochromic. So this is the terms that been used in the UV data analysis. So we found out that why actually the B3 couldn't produce the important electronic transition of the N to pi transition of the carbonyl moiety there, whereas B3 can produce. So if we can see between the structure, this is isotherapeutic, we don't have problem with the execution of simulating or modeling their CD spectrum, because there is no interaction in space between the N electron. The one that been colored in red here is the oxygen, and the one that been colored in blue here is the nitrogen. So they are very far in space. They cannot interact. This one is very far as well. Similarly to this one, this is our carbonyl in the ester moiety, and this is the carbonyl in the oxindole moiety. So they are very far. No wonder that we can use B3 lips to get the to produce the electronic environment in the orbitals of the molecule inside there. But for the theropodid, in the conformational 3D, this is the carbonyl of the oxindole. That is the carbonyl of the alpha beta unsaturated methyl ester. So these two electrons are very close in space, means that this particular carbonyl, they can transfer electron. The electron from here can jump to this particular carbonyl, and this carbonyl can give the electron here. So, sorry. So that's why that the CAMB3 lip is very important in getting the information for the theropodin and not in isotherapodin. So this is called actually the doubly carbonate transition in space in a theoretical manner. So this has actually been proven by the orbital, the HUMO to LUMO molecular orbital data analysis of the two compounds. If you can see here, I'm focusing at this region. The one that colored here, like candy there, gummy bear there, is actually the orbital. Orbital is a location where the a region, a moiety where the electron is located, high probability they are located. So when the electron is there in the orbital, so we know that the electronic transition is actually due to this particular region. So for the B3 lip, for this one, for this region, this is from the HUMO to LUMO. So for the first conformer, this is for the second conformer. They actually are from orbital 98 HUMO, high occupied molecular orbital, and excited to low unoccupied molecular orbital in the molecular orbital of 100. This is also in the 100. That's why it failed to predict the electronic transition of our carbonyl just now. But yes.
We are already 70 minutes past 11, so you might want to read out a bit. We are already 17 minutes past 11. Thank you.
Okay. So we're going to finish. We still have, 5 minutes. I can finish this one. Okay. Sorry for that. So in the CAMB3 lip, actually the orbital that's been counted is the 99 orbital. This is 100. So no wonder that in the CAMB3 lip, it can produce the crucial N to pi transition of the carbonyl structure where B3 lip couldn't produce. So from there, we decided that we're not going to use our B3 lip for for model the structure of our 3 new compound in hand, we want to use chem-butyryl because we know that we also have the same moiety there. We have the carbonyl and we also have the carbonyl from the ester. This one as well, these two. So we wisely choose the chem-butyryl. We did all the same things and then we got this one. So by having the similar electronic transition for the 3 compounds, then we establish the absolute configuration of our compound. Isoformational, this is all the configuration. So the S, 15S, 16R, 17R, 19R, and 20R. This is very more full. Okay, and the longifluorine is 4S, 8R, and 9S. So between isoformational and formational, they are only differ at the configuration of C7 or this should be 7R. Okay. So this the study that been done is published in a flagship journal for natural product recently in Q1, Journal of Natural Product. And acknowledgement, I like to acknowledge Atta Rahman Institute for having me as a researcher there and giving me research platform, and Faculty of Pharmacy, UITM, for the ECD, because the ECD is down there in level 8. And then Research Management Institute, RMC, UITM, for providing the GIP grant. Actually, this is a very, the grant really helped the student because the student is supported by the grant and he managed to graduate on time. And thank you to Prof. Datin Rohaya Ahmad. So she had helped a lot in supporting and the other things as well, and all who are directly indirectly contributing to this work. And this is this work is actually dedicated to my postgraduate student, especially Mr. Yusri. So this is Yusri. He just graduated, so he's the quantum chemist here, and the other student of mine as well. So I like to end my talk with a phrase by Niels Bohr. He said that if quantum mechanics hasn't profoundly shocked you, so actually you haven't understand it yet. So I really amazed the knowledge that we can have from the quantum that we can embed in our experimental analysis to help to reduce the time, to reduce our energy, to reduce the material in order to establish the absolute configuration of the molecule by using quantum mechanics calculations. So that's all. Thank you.